Hello, my name is Peter Claydon. I'm president of Picocom. I'm going to talk to you today about some of the challenges of creating SoCs for 5G networks. I'm joined today by Gajinder Panesar. Gaj was CTO of UltraSoc when this project started. UltraSoc has been acquired by Siemens and Gaj is now a technical fellow there. Picocom is a semiconductor company and we're developing SoCs for 5G new radio small cells. Our products can be used in lots of different applications, but our particular focus is in building, which is what I'm going to be talking about in the first few slides of this presentation. One of the new features of 5G is that in the radio access network, what used to be a single base station, or eNode B, can actually be split into lots of different units. In this picture here we show how this may be in a city application. So we see there the radio units, which can be quite small units mounted on every floor of a building. At the bottom within the building there, the distributed unit, or DU, and then going back through the fibre network to a central unit, which is likely to be in a secure location somewhere. So we see here a graphic showing two potential types of deployment in buildings. In building A, there are just most of the electronics is contained in a single radio unit, and in building B, there's a distributed unit with most of the electronics going up to simpler radio units. One of the key things about this sort of 5G deployment is it allows an open RAN deployment where there are standardized connections between the units defined by the O-RAN Alliance and the Small Cell Forum. And all these connections use Ethernet rather than proprietary implementations for their connectivity. Picocom is developing SoCs for various parts of this system and various modes of deployment. Our first SoC, which we're going to talk about here, can be used in more integrated radio units that we see in building A, or a cluster of them can be used in a distributed unit in building B. So now let's look at the architecture of this chip in some more detail. The SoC has two primary interfaces used for communications. It's a PCI interface, shown here on the right, and an Ethernet interface on the left. We use two clusters of ANDI Swiss5 cores for protocol level processing associated with this interface and various other tasks. The primary DSP functions in the SoC, which make up most of what it does, are undertaken by a cluster of CEVA XC12 cores working in conjunction with some hardware accelerators. And of course there's a lot of memory, both SRAM, which is distributed throughout the SoC, and a shared DDR4 interface. And it's all connected together by an Arteris NOC. 5G baseband processing is a lot more difficult than 4G from LTE. So why is it so hard? Well, firstly, 5G is far more flexible than 4G. As in 4G, most processing is performed in slots. A slot is 14 OFDM symbols. But in 5G, these slots can be configured in various different lengths, from 31.25 microseconds all the way up to the millisecond that was used in 4G. Processing for the next slot generally takes place in the current slot. And uplink and downlink processing is done at the same time. But in 5G, there are far more different slot structures than there were in 4G. To add to this, some processing must be done in much shorter timescales. One particular example is URLLC, ultra reliable low latency communication, where the key term here is low latency. Low latency communications here, data can arrive in either the uplink and downlink at pretty much any time and has to be processed immediately regardless of what's going on in the rest of the SoC. To add to this, one SoC can support many antennas. These may be MIMO antennas related to one cell or for completely different cells. And where they're completely different cells, they could be for different mobile operators which may have their own software and their own parameters. We also have to take care of Open RAN, which is standards compliance, maintaining plug and play with different things that our unit may be connected to. And with all this going on, there are likely to be more frequent upgrades in the field. So, what could possibly go wrong? Well, there were some clues in the previous slide. There are so many things happening all at the same time. There are dozens of individual processors and hardware accelerator blocks in this system, and they're all dependent upon each other, even if they're not supposed to be dependent on each other, as they're all sharing the same NOC. So what happens if something is late? In this example, some processing earlier in the slot has been delayed, which has caused other things to be delayed. Now that earlier processing may have been as a result of a cache miss in a different part of the system, causing some data to be delayed. So if that processing overall overruns the slot boundary, the whole system may fail. Now the system is designed to cope with this sort of failure, but at the very least you'll lose all the data that was meant to be going through in that slot, and that's not a very good thing to happen. Now these problems are very difficult to detect in the lab. For once, if you alter the code, it alters the timing of the entire system, so you may not be able to detect what's wrong. I think we all know systems where the code in the production system has been left with some of the debug features in because it will only work in that way. Now the problems may only actually occur every few minutes or every few hours, and only under certain circumstances which are difficult to reproduce. But it can be even worse in the field. The problems can only happen after years, and this may be, for example, because of a software upgrade, or it may be because of an upgrade in a different part of the system. So you need to get this information back and to be able to analyze it. So to help with these problems, I went to my friend Gaj at Siemens and asked if their embedded analytics technology could help with our problems.
Thank you, Peter. It is a very interesting and complex system that you're building. An SoC that will support many hundreds of users at the same time, many operators who will have their own software, and that software will need to change to track the evolving 5G standard. This is quite a complex beast that you're building. And for such complex beasts, there are a number of areas that may cause problems in performance and functionality. I've listed a few here that we all know about. Caches. The caches are unpredictable, and the performance of the cache miss latency is an issue. Systems sometimes hang or deadlock, and it's not always clear what's going on when that happens or what led up to that. Loss of performance in the CPUs primarily. And this isn't necessarily an underpowered processor, but it's the interaction of software with other components in the SoC. The dimensioning of the NOC is also another area that can cause performance and functionality issues. Memory accesses, now not just memory bandwidth, which in itself is something that to be concerned about, but the pattern of accesses, the number of masters accessing at the same time, the frequency of accesses, all these things will add to the mix of problems that could come in this system. So what's required is the ability to observe the behavior of the target system without affecting it in any way. I'm going to run through the Tessent Embedded Analytics architecture and product range, which can do just that. I'm doing this in the context of a generic SoC system, which you can see here colored light blue. Embedded Analytics provides 4 classes of hardware IP, all delivered as Verilog for instantiation into the SoC design. The first category we call analytics modules. We have a portfolio of them, but for the moment I'm just showing 2 of the more complex ones in the teal color or green-blue color. The one on the left, the bus monitor, this is a protocol-aware and transaction-aware monitor. It observes transactions going from masters and managers to the interconnect and from the interconnect to the subordinate slave nodes, and responses from the subordinates to the managers. The bus monitor has a number of features such as the ability to count transactions and the ability to calculate the duration for completion of a transaction. It can do things like min, max, average. It can do that in a window of time. It can capture trace of the portion of the interconnect that it's observing. The status monitor on the right has similar capabilities in that it has a windowing system, it can do metrics, it can capture trace, but importantly, it doesn't know what it's connected to. So at runtime, you would need to say, look at this signal, and if it has this behavior, then look at that other signal and capture the trace or count values, and so on. The data these modules generate goes onto a message passing fabric, and the message passing fabric is orthogonal to the target system, as you can see, which means that you do not affect the target system behavior with the data that our monitors generate. The message engines and the message fabric are not just used for data transport, but also for cross-triggering events between one or more monitors at the same time. Which monitors cross-trigger with which other monitors can be configured at runtime, meaning that at RTL time, you don't have to dedicate a whole bunch of wires for cross-triggering. You can do this at runtime, and the protocol within our message passing fabric allows you to do that with great ease. Ultimately, the data is transported across the message passing fabric and ends up to the third class of IP blocks. This is a family of communicators. We call them this because they communicate with the embedded analytics world with another world. Here I'm showing in the middle a USB 2 communicator which provides USB 2 communication completely in hardware. There's no software required, no software stack to run on the target system. From cycle 0, you're ready to be able to configure and accept data from the embedded analytics modules. We have an EBC communicator which allows communication with the system's USB 3 controller, so high bandwidth trace which is only present when the target system is in mission mode. That data will be transported using USB 3. We have an Aurora communicator. Then on the left we have something called an AXI communicator. What this does is allows a CPU on chip to be able to access the teal or green and blue modules for configuration, but also to be able to capture data that these monitors generate so that any analysis can be done by a CPU on chip that's part of the target system. And of course, we have a way of using system memory to pour high bandwidth data into, which can be trickled out slowly at some point later. We have in development an analytics subsystem which will encompass a CPU. All of the other modules I've shown have no CPUs. They're all hardware engines. The analytics subsystem will have a CPU that will be tuned to do analytics within the target SoC. And then we have a bunch of other modules like the static instrumentation and DMA modules that can be used to push and pull data from the system. The fourth class of IP blocks that we have are things we call active managers. All of the other blocks we've looked at don't affect the target system, but there are a class of problems where you do want the monitoring system to affect the behavior. We have a thing called the bus sentry, which observes transactions in a very similar way to the bus monitor, but in this case the transactions go through the bus sentry. And then when we see some anomalous behavior or some transactions that are erroneous, we can not only detect that and alert the system, we can also prevent that transaction or those sets of transactions from taking place. We also have in development a lockstep manager, which is shown here looking at the RISC-V cluster, but this can be applied to any CPU, not just looking at transactions coming out of the CPU, but also looking at the internal signals within a CPU. So basically, this is a tracker system. It could be used for CPUs, it could be used for neural nets, or it could be used for observing state machines. We have CPU-centric monitors. These provide classic run control, which is clearly intrusive, but that is by design. You want to be able to stop and start CPUs and understand how the CPU is behaving. And then there are ways of accessing trace information from the CPU. And then finally, we have a way of locking down the system. So that's what these white blobs are. These are locks which a trusted environment on the chip can lock or unlock, which would then prevent visible access to certain parts of the SoC and hence deny or allow visibility of that section of the system. Okay, great. So that's the monitoring architecture. So how does it map onto Peter's Picocom SoC architecture? We instrument the SoC with the embedded analytics monitors and the infrastructure, which you can see again in the lovely greeny blue color. We have some of the modules that we talked about earlier. For example, we have the AXI bus monitor. Remember, that's a transaction-aware monitor that observes transactions on the interconnect. We have a status monitor, which is a little like a logic analyzer. We have the XI communicator that allows one or more processors in the SoC to access the embedded analytics infrastructure. We have the SMB, that's the system memory buffer, which allows us to use some of the system memory for storage of data that we generate. And we have the USB communicator, which, if you remember, provides USB 2 completely in hardware. Now, I'm going to show some examples of the sort of observation that these monitors can provide and the data that they generate. And then I'll go on to describe how that can be used for on-chip in-life analysis. In this example, we're going to use one of the bus monitors to look for a deadlock condition or a system hang condition. In this case, a transaction starts but never completes or doesn't complete in a specified time. To do this, we configure the bus monitor at runtime to look for transactions completing within the time. If that time expires, then the bus monitor will have captured within its internal buffers the sequence of transactions leading up to it. Now, the bus monitor will be able to alert the system or the analytics CPU, and the contents of the internal buffers within the bus monitor will give you all the transactions before that condition happened. In this example, we reconfigure the same bus monitor as in the previous example, but this time we're going to look at iCache behavior of one or more of those CPUs. We can configure the bus monitor to count the number of iCache misses coming from one or more of those CPUs in a window of time, which is also configurable at runtime. And from that, you can infer a number of things like the efficiency of your branch predictor or the efficiency of the placement of code that you have. But I think in this particular case, the duration for the completion of your cache miss is much more important. So we can get the bus monitor to calculate the min-max average duration of the cache traffic. And clearly, it's the maximum cache traffic that will have an impact on the performance of that CPU, because that CPU is waiting for the instructions to come back and can't do anything until that's arrived. And this will have an impact on the performance of the software of the whole system. In this example, what we're going to look at is the access patterns going to SRAM. In this case, what we're going to do is configure the bus monitor closest to the SRAM to look at transactions originating from 4 masters to the CEVA DSPs and to the RISC-V cores. And we get the bus monitor to calculate the min-max average bandwidth going to that SRAM. And we can see in that window where the red rectangle is that all 4 accesses arrive in that window, which means we're getting more than 2 gigabytes worth of access arriving in that window. Now, if that happens regularly, then you're maxing out the bandwidth, the SRAM, and potentially causing bottlenecks and performance issues of the whole system. What we saw earlier was some of the capabilities of some of the embedded analytics modules. What I want to do now is to give you an idea of how those capabilities can be used in life, in the field, to monitor how the system is behaving. To do that, what we can do is have one of the CPUs and load some analytics software on that. It will get data from the embedded analytics infrastructure via the AXI communicator. And in this simple example, I'm going to show you how the static instrumentation module can be used by the software executing on the system and the hardware accelerators to give an indication of how the system is performing. Peter showed very early on that there are strict timing constraints within 5G and indeed many other wireless systems. So these timing constraints are known at compile time. More than that, the tasks that need to be done are also known at compile time. So both those two things can be given to an analytics software to say that when this happens, then these are the sequence of things that should take place within this time window. So if the flow diagram that you see there is the desired program flow within the timing budget, we can use the real-time information that we gather while the system is running to make sure that what is actually executing is correct. So for example, if the data that we collect from the static instrumentation doesn't match the program flow of sequence that it should be following and doesn't match, or doesn't match the timing constraint, it may be following this program flow as shown by this flow diagram, in which case the analyzer CPU knows there's something wrong and it can alert the system's CPUs. We can augment the information that the static instrumentation modules give us with some of the information that I showed you in some of the earlier examples. And in this case, the modules themselves can generate alerts for themselves. And these alerts can go both to the system CPUs, but more importantly, it can go to the analyzer CPU, which can then perform some sort of causality detection and then alert the system saying this is going to fail and for these reasons. So one such example is that the status monitor could be used to observe the frequency of data structures being fed into the accelerators. And as this approaches a threshold, that monitor can be used to alert the analyzer CPU, which can then take that into account when it's doing the analysis of the behavior of the whole system. And of course, another example is to have the bus monitor to keep track of the number of outstanding tractions in flight. And when that approaches a threshold, it can also indicate to the analyzer that this is going on. And so the software running on the analyzer CPU can say, well, you pushed out your timing budget because of these reasons. So just to explain it in a different way slightly, is that if we take the timing diagram that Peter showed earlier, we could have the FFT, the channel estimator, and other tasks that do statically that are statically instrumented, though that information ends up at the analyzer. But we also have the bus monitor doing things like the min-max average calculations. And you can see in this case that the channel estimator, when it slips and it overruns, that information is very useful to the analyzer CPU, and because it will have the data from the bus monitors and the status monitor looking at the number of data structures being fed into the accelerators, it can calculate that the PUCCH will overrun the time slot. And the failure for that is that too much bandwidth into the SRAM, and as a consequence of too many data structures being fed into your accelerators. So Peter, that's quite a lot of detail. From your point of view, is this a reasonable approach to instrumenting your system and doing corrective action?
Yes, thanks, Gad. That's a very good answer. And one of the things I like about it is it applies to hardware as well as software. On an SoC like this, we have a lot of hardware accelerators, as we've seen from the diagrams. And this is because although we'd ideally like to do everything in software, there's a balance to be struck between the silicon area and hence the price point we're designing to, and in fact the power dissipation that we have to meet, and the configurability. So a lot of traditional methods of analysing what's going on, for example using watchdog timers, really only apply to the software element of the system. And using embedded analytics like this, we have something that we can apply to both hardware and software at the same time. So to summarize, it's very complicated. 5G small cells that use Picocom SoCs could be supporting hundreds of users. And if you think back to the diagram of the building that I showed you earlier on, you would have one centralized resource made from our SoCs that is supporting a number of different radio heads. And these may not be just from one mobile operator. In a neutral host case, you could have several different mobile operators, possibly with different software. So managing this is very hard. The chip's complex. And we have many different independently sourced IP blocks. Some of these we've developed ourselves, but others that we've sourced from external IP providers. And then, of course, there's a NOC which stitches everything together. And we need to be able to monitor these not just individually as you might with a traditional processor, but all at once together so we can find out how one part of the system is affecting another part of the system. And we need to be able to do these as standards evolve and software is upgraded over a period quite likely of many years.
This is a classic case of systemic complexity. You're squeezing a lot of things into one SoC, tracking emerging standards, and the fact that you're allowing operators to put their own software down, and over time that's going to change. That completely adds a different dimension to this complexity. For that, I think you do need this non-intrusive monitoring. The embedded analytics which I've described will evolve over time. As you learn more about how the system should behave, you'll be looking at the patterns of accesses, not just where things are breaching their timing boundaries, but looking at whether this is the correct sequence of accesses in a certain window of time. So from that, you will learn an awful lot in terms of the analysis methods.
I know, Gad, you've got a lot of excitement about this in the automotive market because of the safety and security aspects of it. Now, though 5G doesn't have the same safety and security aspects as automotive, there are some aspects of it that are fairly critical. For example, the ultra-reliable low-latency communication systems that I was talking about earlier. Now, in these, you have to be able to analyze what's happening and fix any problems.
Yes, there's the security layer as well. 5G has security built into the standard, but system-wide security is also important. And this is something embedded analytics helps with. If something's doing something that it shouldn't be, or something hasn't been doing something that it should be doing, the analytics can provide an insight into whether a CPU or a set of CPUs has been compromised.
Yes, one of the keys to this is that traditionally engineers pipe a tremendous amount of trace information off a chip in order to be able to analyze it in a lab environment. By using the embedded analytics philosophy, all that analytics is taken from the lab and put onto the SoC, which then enables you to actually transport all of that analytics into the field as well.
In your case, the systemic complexity that you have, just observing what's going on inside a CPU is not going to give you an indication of what's happening in the rest of the SoC. I think the problems in code running in the CPU is probably orders of magnitude less than the pain points you could have when accelerators and all this other stuff are working together.
We know we're going to get bugs in the field. I can remember, for example, in a previous life, we were working with a big global mobile network operator, and it was getting towards the launch of their system. And this included a 4-user small cell. And in that, if you'd had 3 of the users were having on calls for maybe 10-15 minutes or more, when the 4th user joined, the whole system crashed. It took weeks for engineers working long hours and weekends to find what the problem was. And when they found it, it was a single character change in the source code. Now that sort of thing is really difficult to find.
I remember something similar when I was working in the wireless market. There was a problem that only occurred when the user was traveling at speed and doing a handover between cells. That is something you can't replicate in the lab. So having these introspection probes in the field, gathering that data to find out why this problem happened, would have been very helpful. As it was, we didn't, and it took us 3 months to find that problem.
Thanks everyone for listening. So that's goodbye from Gadge and me, but please let us know what you thought of the presentation and if you found it interesting. Goodbye. Thanks everyone for listening. So that's goodbye from Gadge and me. Please let us know what you thought of the presentation and if you found it interesting.